Alright, welcome back to another video. We're gonna actually talk about iron catalyst in this video. So let's get started. So before we get started, we're actually gonna talk a little bit about the history behind iron catalyst. So in 1905, a German chemist named Fritz Haber reached an objective long sought by many chemists, that of fixing nitrogen from air. Atmospheric nitrogen, or nitrogen gas, is relatively lacking and does not easily react with any other chemicals to form new compounds. Using high pressure and a catalyst, Haber was able to directly react nitrogen gas and hydrogen gas to create ammonia. His process soon scaled up by BASF's great chemist and engineer Carl Bosch and became known as the Haber-Bosch process. Considered by many as one of the most important technological advances of the 20th century. Haber's breakthrough enabled mass production of agricultural products. Fritz Haber's synthesis of ammonia from its element earned him a 1918 Nobel Prize in Chemistry. So to begin this, I actually have a short video that I would like to show first. So I'm gonna play it right now.
You have likely produced ammonia in the laboratory from the thermal decomposition of ammonium chloride or from the reaction of ammonium and hydroxide ions. Have you ever wondered how ammonia is produced on an industrial scale? In this lesson, we will learn about the Haber process to produce ammonia, developed during World War I by Fritz Haber and Carl Bosch. For their efforts and contributions to developing large-scale industrial processes, they were awarded with Nobel Prizes in chemistry. The Haber process is the industrial process for the manufacture of ammonia from hydrogen and nitrogen. Hydrogen is obtained from the reaction of methane and steam, producing carbon monoxide as a byproduct. The hydrogen produced from this reaction also reacts with oxygen from air, producing water and leaving nitrogen behind. Recall that air is 77% nitrogen. These gases are then compressed and delivered to the reactor, where ammonia is produced. These gases are then cooled down and ammonia is liquefied, ready to be tapped off. Unused hydrogen and nitrogen are recycled back to the reactor. Let's revisit this reaction again. Note that this is a reversible reaction and that the forward reaction is exothermic. The Haber process uses Le Chatelier's principle to maximize ammonia production while keeping operating and production costs in mind. Le Chatelier's principle tells us that increasing pressure will favor the side with fewer moles. For our case, the production of ammonia. It would make sense to conduct the reaction at a very high pressure, but we must also remember that it is expensive to build and operate a plant that can withstand such high pressures. Therefore, a compromise pressure of 200 atmospheres is used. Let's keep Le Chatelier's principle in mind. What do you think is the best temperature conditions to maximize ammonia production? Please pause the video to think about this and resume once you are ready. Since the forward reaction is exothermic, it would make sense to conduct this reaction at a low temperature. The compromise temperature is 400 to 450 degrees Celsius, which is not exactly low, but not too high. If a low temperature were used, the rate of reaction would be very slow, though the exothermic reaction would be favored. It would actually take a long time for equilibrium to be reached, so a compromise temperature of 400 to 450 degrees Celsius ensures that the reaction proceeds with sufficient yield. The yield of this process is 10 to 20%. Remember from the introduction that unused gases are recycled, so no reactants are wasted. As well, an iron catalyst is used in this process. The presence of the catalyst does not affect the position of equilibrium, but increases the rate at which equilibrium is reached. In conclusion, the Haber process is the industrial process to produce ammonia from hydrogen and nitrogen. It is conducted at 400 to 450 degrees Celsius and at 200 atmospheres in the presence of an iron catalyst. These are compromise conditions in order to maximize ammonia production and economic profit.
I hope you enjoyed that video and have a further idea of what we're going to be discussing throughout this entire project. So to further explain Haber's process, it describes the process of manufacturing ammonia from nitrogen and hydrogen, and then goes on to explain the many reasons for the conditions used in the process. It looks for the effects of temperature, pressure, and catalysts on the composition of the equilibrium mixture, the rate of the reaction, as well as the economics of the process. So over here we have the chemical equation for ammonia. So there's nitrogen and hydrogen, and they are derived mainly from the natural gas of methane and become ammonia. And here, this is where the iron catalyst is held, which becomes ammonia. So the reaction is reversible. You can actually break down ammonia to get nitrogen and hydrogen. And this process is exothermic because over here you can see we have the production of creating ammonia. We have nitrogen and hydrogen. They bond together and they're compressed in the iron catalyst at a certain pressure and temperature, and they release out a liquid ammonia. And the unreacted gases recycle back into the cycle of the process. So how does it change the industrial reaction it's involving? Well, in order for ammonia to be created in a catalyst, there has to be certain factors that must meet the expectations. Some include the proportion of the hydrogen and nitrogen, temperature change, pressure, equilibrium considerations, rate of change, the catalyst itself. All these factors play a major role in the production of creating ammonia, which now leads to the big question. What is the benefit of creating ammonia for society, or the environment, or the industry itself? Well, good question actually. About 90% of ammonia is produced to use for fertilizers. It helps sustain food production for billions of people around the world. The production of food crops naturally depletes soil nutrient supplies. So in order to maintain healthy crops, farmers rely on fertilizers to keep soils productive. Fertilizer also can help us increase levels of essential nutrients like zinc, selenium, and boron in food crops. My next topic is going to be on household cleaning products. On its own, or as an ingredient in many household cleaning products, ammonia is actually used to clean a variety of household surfaces, like tubs, sinks, toilets, bathrooms, kitchens, you name it, countertops, and tiles for the floor. So ammonia is also effective at breaking down household grimes or stains from animal fats or vegetable oil, such as cooking grease and wine stains. Because ammonia evaporates quickly, it is commonly used in glass cleaning solutions to help avoid streaking. In addition, it can also be used in industrial and manufacturing uses. Ammonia can actually absorb substantial amounts of heat from its surroundings. So this means that you can actually it can be used in refrigerant gas and in air conditioning equipment. So ammonia can be used to purify our water supply. But hear me out on this one. It actually can be found in our daily products, including plastic, fabrics, pesticides, and dyes. So thank you for your time. And hopefully you learned something new in this video. I try my best to be as clear and precise as possible. But make sure to like the video. And hopefully I get to see you again. Bye guys.